Ah, okay. Um, all right. So if I remember correctly, did we stop here? Was this the last thing that we did? Did we do this example here? I think I remember doing this one, but not this one. Yeah. Okay. So let me copy and paste this so that we have space to work with. So let me all right. So this question is kind of similar to the previous one, where you're given the composition data, and again, you're asked to determine the empirical formula, right? So if you remember what we said to commence with a question of this type, we assume that we're working with 100 grams of the substance, so each of those numbers would represent a mass present in 100 grams. So you know me, I like to do things in a tabular fashion. All right, so at the top, I'm going to have carbon, hydrogen, and oxygen. And then the first row will contain the mass data. So basically, we're just going to express these percentages as mass. So here we're going to have 45.27 grams. For hydrogen, 9.50 grams. And for oxygen, 45.23 grams. All right? Now, can anybody remind us of what the first step would be after we write down the grams values for each of these? What's the next step? Feel free to look into what we did for the previous example from last class. What do we do? Exactly, we calculate the moles, right? So for each of these, we divide each of them by their respective molar mass. So in the case of carbon, that would be 1 mole over 12.01 grams. In the case of hydrogen, that's 9.50 grams multiplied by 1 mole over 1.008 grams. And in the case of oxygen, it's 45.23 grams multiplied by 1 mole over 16.00 grams. And so let's work out each of these. So in the case of carbon, that would be 45.27 divided by 12.01. And according to my calculation, this works out to be equal to 3.769 moles. In the case of hydrogen, we divide 9.5 divided by 1.008, and that gives 9.41, I'm sorry, 9.42 moles. And then in the case of oxygen, that would be 45.23 divided by 16. And according to my calculation, that works out to be equal to 2.827 moles, all right? Okay, so those are the mole values for the respective elements. So what would be the next step? Based on what we have done before in the previous example.
You would divide each of those by the lowest mole.
Right, so you identify which of these will be the lowest value, which is this one right here. And you're going to divide right through by 2.827 moles, right? So here we're going to have 3.769 moles divided by 2.827 moles. Here we're going to have 9.42 moles excuse me, divided by 2.827. And here, that divided by itself will give you 1, right? So let's see what would be the result of dividing these. So in the case of carbon, that would be 3.769 divided by 2.827. And according to my calculation, I got 1.333. In the case of hydrogen, 9.42 divided by 2.827. And I got 3.332, right? Now, in this particular case, unlike the previous example we worked with, if you remember when we got to this stage in the previous example, we got a number that was close to an integer. I don't remember exactly what the numbers were, but I remember them being close to integers, right? So in that particular instance, we can round off to the nearest integer. In this case, however, we can't do that because, for example, the 1.33 is too far from 1 for us to just simply round it off to 1, right? Same thing is true here for the 3.332, right? So the question now becomes, okay, what do we do at this stage? And in this particular case, what we do is we try to identify an integer that when we multiply each of these numbers by that integer, you're going to get a number that is close to an integer. And it turns out that the number that you multiply this by would be 3, right? And I'll explain why I know it's 3 later on. But for now, if you multiply right through by 3, well, let's start off with the carbon. So if you multiply 1.333 times 3, you're going to get 3.999. And if you multiply 3.332 times 3, you're going to get 9.996. And then if you multiply 1 by 3, you're going to get 1. So you notice now that 3.99 and 9.996 are both relatively close to the nearest integer. So you can approximate this to 4, and you can approximate that to 10. And therefore, the empirical formula would be C4H10O3. And that's basically how you would do that, all right? Now, why do we use 3 here? Well, the hint that would point me in that direction is the fact that you have a recurring 3 after the decimal point in both the case of carbon and hydrogen, even though there's a 2 here, but that's close to a recurring 3, right? So if you have a recurring 3 after the decimal point, you simply multiply everything by 3. And as you can see here, when you do that, you end up with numbers that are close to the nearest integer, all right? So there are some situations where you can, make a reasonable guess as to what you should multiply right through by. In fact, let me just give you a little, well, let me ask you, are you finished with this here? Can I clear it? Yes, no, maybe so? Okay, let me clear this. And let me just construct a little table here, which is kind of like a guide for predicting what you'd multiply by to get the nearest integer if you face a situation like the one that we just looked at. So if you have, okay, okay, if you have a digit of 5 after the decimal point, then basically you multiply by 2 to get the nearest integer, right? If you have a 2.5 after the decimal point, you multiply by 4. If you have 0.75, you multiply by 4. If you have the one we looked at, recurring 3, multiply by 3. If you have a recurring 6, you multiply by 3. If you have a recurring 1, multiply by 9. And those are the ones I can think of right now. Now, in other situations, basically you have to do a trial and error thing, all right? Try different numbers to see what you'd multiply by to get the nearest integer, or an integer that or some number close to an integer, all right? So that's why I recognize that in the case of the example that we just looked at, I realized that there's a recurring 3 after the decimal point, so I knew that you need to multiply by 3 in order to convert that number into a number that's either an integer or close to an integer, all right? Okay, any questions about that example? Any questions? All right, so back to the PowerPoint. So let's see what's next. Okay, so again, this is something you should have met before in your introductory chemistry, and that is the relationship between the molecular formula of a compound and the empirical formula, right? And if you remember, the molecular formula gives you the number of atoms of each element present per molecule, while the empirical formula gives you the ratio of the atoms of the different element present in the compound, right? And as such, as a result of those two definitions, one can clearly see that there's a relationship between the molecular formula and the empirical formula. And the relationship between the two is an integer, right? So it could be 1, 2, 3, whatever, right? So just to show you an example, let's say you know that the empirical formula for a compound is CH2, right? What that means is that the empirical formula, or I should say the molecular formula, can be CH2 or C2H4 or C3H6 or C4H8 and so on. It all depends on what the integer is, right? So how do we determine the integer? Basically, we determine the integer by dividing the molar mass of the compound by the empirical formula mass. The empirical formula mass is simply the sum of the atomic masses of all the elements present in the molecule, all right? Or I should say, the sum of the molar masses of the elements in the empirical formula, not the molecule, but in the empirical formula, right? So if you take the molecular formula mass divided by the empirical formula mass, you're going to get an integer. And if you don't get exactly an integer, you're going to get a number close to an integer like, 4.99 or something like that, all right? And then once you get that integral factor, you're going to multiply each of the subscripts in the empirical formula by that number, and that will give you the molecular formula, all right? So that's basically the relationship between the empirical formula and the molecular formula. It's the integral factor, all right? And just to show you an example of how this works, you're given this question where the empirical formula is C3H3O, and the molecular mass is 110 AMU. So the question is asking for the molecular formula. The first thing I would find is the molar mass, which is 3 times, I hate reading, 3 times 12.01 grams per mole. That's for the carbon, plus 3 times 1.008 grams per mole. That's for the hydrogen, plus 16.00 grams per mole. So when we add these together, let's see what we get. So 3 times 12.01. So that's 36.03 plus 3 times 1.008. Oops, 1.008. And then I'll add to that 16. And the answer I got is 55.05 grams per mole, right? So to get the integral factor, that would be equal to the molar mass, which is 110 grams per mole, divided by 55.05 grams per mole. And let's see what that gives. So 110 divided by 55.05. So that gives basically 2, right? So that's the empirical formula. I'm sorry, the integral factor. So to get the molecular formula, that would be equal to C3H3O, all multiplied by 2. So the final answer is going to be C6H6O2. And that's how that is done. All right? Okay, any questions about this one? Any questions? Okay. Moving along. All right, now here's something that I don't think you'd have met in your introductory or high school chemistry. And this has to do with the question of how do we determine experimentally the percentages of different elements in a compound, right? So we call this elemental analysis. Now, what I'll be paying attention to are organic compounds. How do we determine the percentage composition experimentally of organic compounds, right? And I don't know if you know this, but organic compounds are basically compounds of carbon, right? And these compounds will contain carbon, will also, in most cases, in fact, in all cases, will contain hydrogen, and in some cases will contain oxygen and other elements, right? So the method that I'm about to get into is one where we can determine the percentages of the carbon, hydrogen, and oxygen in the organic compound that is undergoing the analysis, all right? So basically the way this works is that you burn the compound in air, all right? And as you all should know, any compound that is organic, when burnt, will produce two products, always, it doesn't matter what the formula is, will produce carbon dioxide and water, all right? Now, the carbon in the carbon dioxide will come from the carbon in the original compound, right? And the hydrogen in the water will come from the hydrogen in the original compound, right? So if you could find a method of trapping the carbon dioxide and trapping the water and determining their masses, then you can determine the mass of carbon present in the carbon dioxide and the mass of the hydrogen in the water, and those would be the same masses in the original compound, right? And then once you determine those masses, you can find out the mass of any additional element like oxygen, and then from there you can find the percent composition, all right? So as I said before, the carbon dioxide and water would be trapped and weighed, and therefore based on their masses, you can determine the mass of the carbon and hydrogen present in the original compound by working backwards, all right? So that's just basically a kind of, word description of what this experiment is all about. Now, the next slide gives a schematic representation of the setup that you'd use to carry out this type of analysis, all right? So let me just go through and explain what is happening here in this setup, right? The first part, this compartment here, is the furnace, right? This is where your sample is going to be located, okay? So basically what you're going to do experimentally is that you're going to weigh the sample, right, before you put it in the furnace, right? Make sure you record the mass, and then you start heating. So when you heat it, the compound, if it's organic, as I said before, will produce carbon dioxide and water, right? So the carbon dioxide and water will be shunted from the furnace into this compartment, all right? Now, in this compartment, you're going to have a substance which will absorb the water that was produced from the furnace, right? Magnesium perchlorate is the substance being used here. And there's another substance which I can't recall right now, which is oftentimes used in this process, all right? So the purpose of this magnesium perchlorate is to absorb the water. So what you would do experimentally is that you would weigh, before you start the experiment, you would weigh the magnesium perchlorate, and then you put it in the compartment so that when it absorbs the water, you can weigh it again, and the difference between the two masses would give the mass of the water, all right? So one important aspect of this part of the experiment is that you must have sufficient magnesium perchlorate to absorb all the water that is produced from the furnace, right? If you don't have enough, then some of the water will escape into the other part of the compartment. So you have to ensure that you have enough magnesium perchlorate present in that particular compartment so that all the water that is produced would be absorbed by the magnesium perchlorate, all right? So that's what happens here. So if you do that, if you did everything properly and make sure that you have enough of this here, then the only thing that should be emerging from here would be the carbon dioxide. And that is led into another compartment which contains sodium hydroxide. And sodium hydroxide will absorb the carbon dioxide. So just as you did here, what you do here is that you'd have to weigh the sodium hydroxide before, and then after it absorbs the carbon dioxide, you weigh it again, and the difference between the two masses would give you the mass of the carbon dioxide, right? So therefore, that's what happens in the third compartment, right? And then once you get the masses of the carbon dioxide and the water, then you can work backwards to determine the mass of carbon present in the original compound, the mass of hydrogen present, and also the mass of oxygen that is present, all right? So that's basically what is happening when you're doing this sort of elemental analysis of organic compounds. Now, the next slide is basically oh, sorry, I thought there was another slide here, but let me just go through this quickly. So this is just basically looking at, this type of analysis at the molecular level. So what we have here is methanol, which is the organic compound. And basically what you do is just expose it to heat and an excess of oxygen. And what happens is that the methanol will be converted to carbon dioxide and water, but you still have some more oxygen present. So the oxygen is the excess reactant because you have some of that present. And then, as we said before, you can take the masses of the carbon dioxide and the water to determine the mass of carbon present in the original methanol, and therefore you can determine the percent of each element present in methanol experimentally. Okay, so this is what I was getting to. So we're going to look at this example right here. This is a good example of how you do the calculations associated with combustion analysis. So let me copy and paste here in Word. Okay, so this is the question right here, all right? So it says you're burning 0.1000 gram sample of a compound which contains carbon, hydrogen, and oxygen. And this yields, and it gives you the amount of carbon dioxide and water that is produced. And then it says a separate experiment shows that the molecular mass of the compound is 90 AMU. So you're to determine a couple of things. A, the mass percent of the compound. B, the empirical formula. And C, the molecular formula of the compound. Okay. Now, what I'm going to do is I'm going to do the A part first, right? So how do we do that? Well, what I'm going to do is start off with the 0.1953 grams of the carbon dioxide. And what I'm going to do is find out the mass in grams of carbon present in this much carbon dioxide. So to do that, we start off with 0.1953 grams of carbon dioxide, and then we convert it to moles, right? So to do that, we put 1 mole of CO2 above, and down here, 44.01 grams of CO2 below, all right? So that this goes with that. The next step is where we convert the moles of carbon dioxide to the moles of carbon. So we're going to have 1 mole of CO2 below and 1 mole of carbon above, so that this will go with that. And then the next and final step, because remember, the aim is to find the grams of carbon, right? So the next and final step is that we multiply this by the molar mass of carbon. So that would be 12.01 grams of carbon above, and below 1 mole of carbon. And then this cancels with that. So now we have to do the calculation. So 0.1953 divided by 44.01 times 12.01. And according to my calculation, and please tell me if I'm wrong, but I got 0.0539, no, hold on, wait a minute, 5330 actually, moles of, I'm sorry, not moles, grams of carbon. So this is going to be grams of carbon, all right? So that's how we get the mass of the carbon. And this mass of the carbon here will be the same mass of carbon in the original sample, all right? The next step is to do something similar, but this time we're trying to determine the mass of hydrogen. So they gave us the mass of water here, which is 0.1000 grams of H2O. And the question is asking for you, or what you need to find is the mass of hydrogen in grams, all right? So we're going to start off with the 0.1000 grams of water. We're going to convert that to moles. So that means we multiply by 1 mole of H2O divided by 18.02 grams of H2O down here. This goes with that, and therefore we have the moles of water. Now for the next conversion factor, let me warn you that students learning this for the first time especially makes a usual mistake right here. If you look at the formula here for water, right? What this suggests is that 1 mole of water will contain 2 moles of hydrogen, right? So therefore, to convert from moles of water to hydrogen, we need 2 moles of H above and 1 mole of H2O below, right? A common error that students tend to make at this stage is that they forget to put 2 here. They would use 1 right there, right? So please note, right? Make sure that when you're getting to the stage where you're calculating the moles of hydrogen, make sure that it's 2 moles of hydrogen for every 1 mole of water. And then the next step is kind of similar to what we did here, and that is we calculate the grams of hydrogen by multiply by the molar mass, which is 1.008 grams of hydrogen over 1 mole of hydrogen. And then we work that out. So this will cancel out with that. So let's see what that gives. 0.1 divided by 18.02 times 2 times 1.008. So according to my calculation, this will be 0.011, how many sig figs? 4 sig figs. 0.1119 grams of hydrogen, all right? So far, we have determined the mass of carbon in the original compound and the mass of hydrogen in the original compound. But remember, the question says that there are 3 elements present: carbon, hydrogen, and oxygen. So my question to you is this: based on what we have done so far, how would you determine the mass of hydrogen? Based on what we have done so far, we have gotten the mass of the carbon, we have gotten the mass of the hydrogen, but there's a 3rd element present, that's oxygen. So how would you suggest, excuse me, that you'd obtain or calculate the mass of oxygen based on the information provided?
Subtract 2 hydrogen from the original mass.
Sorry?
Subtract 2 hydrogen from the original mass of the H2O.
What do you mean?
Like, it was given the original mass of the H2O, so you subtract two.
Well, you're given the original mass of the sample, right? But how would you use that to determine the mass of the oxygen along with these 2? Any ideas?
You do 2 separate problems and then add them together.
If you start off with the original mass of the compound, which contains 3 elements, and you have successfully determined the masses of 2 of those 3 elements, then how would you get the mass of the oxygen? Yes, ma'am. You subtract what from what? Okay, so you're saying add this to this, and then subtract it from what? No, not 1.
0.1.
0.1, exactly. So the 0.100 grams, which is the total mass of the compound, you're going to subtract from that, as she suggested, the sum of 0.05330 grams plus 0.01119 grams, all right? So let's do that calculation. 0.100 minus the sum of 0.05330 plus 0.01119. And I got, and again, please correct me if I'm wrong, I got 0.03551 grams, all right? So that's what I got when I calculated the mass of the oxygen, all right? So far we have the masses of all 3 elements. Now the A part is asking for the percentage of each element, right? So basically to find the percentage of each of them, let me start off with carbon. You're going to take the mass of the carbon that we calculated, which is 0.05330 grams, divided by the total mass, which is 0.1000 grams, times 100%. And then let's see what that gives. 0.05330 divided by 0.1 times 100. And according to my calculation, this works out to be 53.30. We do a similar calculation for the hydrogen, which is, what's the mass of the hydrogen? 0.01119 grams divided by 0.1000 grams times 100%. And that gives 11.19%. And then do a similar calculation for the oxygen. That would be equal to the mass of the oxygen, which is 0.03551 grams divided by 0.1000 grams times 100%. And that gives 35.51%. All right. And what I would do for a question like this, since I know that the total percentage should add up to 100, I'll just check to make sure that's the case. 53.30 plus 11.19 plus 35.51, and I get exactly 100%. So I'm pretty confident that those answers for the percentage composition would be correct. Okay, any questions about what we have done so far in the A part of this question? Any questions? Any questions? Okay, so I think I'm going to need some space here. So what I'm going to do is just basically clear all of this here. Okay, so we have answered the A part. Now the B part is asking for us to determine the percent composition. So we're going to need the, I'm sorry, not the percent composition, I'm sorry, the empirical formula. So for this, I'm going to take the same approach as before. I'm going to start off with a table where at the top I'm going to have carbon, hydrogen, and oxygen. And here I'm going to write down the masses, right? Now, in this particular case, you can write down the masses that we calculated in the A part for the carbon, hydrogen, oxygen, or we can use the percent values that we calculated, right? It doesn't matter which one we use, the result will still be the same, right? So what I'm going to do is use the percentages. So I'm going to need you guys to remind me, what was the percentage we calculate for the carbon?
$53.30.
53.30. All right, so I'll express that as grams. What was the value for the hydrogen?
Hydrogen was
11 point,
11.19,
yeah, I seem to remember that. And then the oxygen was what?
35.51.
35.51 grams? Okay, good. So, where it was percent, but we're going to use grams. So, what's the next step? What do we find in the next step? The moles, exactly. So, we're going to take the 53.30 grams, multiply by 1 mole over 12.01 grams. In the case of the hydrogen, it's 11.19 grams, multiplied by 1 mole over 1.008 grams. And finally, in the case of oxygen, it's 35.51 grams, multiplied by 1 mole over the molar mass, which is 16.00 grams. All right? So let's work out each of these. 53.30 divided by 12.01. And according to my calculation, this works out to be 4.438 moles. And then in the case of hydrogen, it's 11.19 divided by 1.008. And I got 11.10 moles. And then finally, in the case of oxygen, it's 35.51 divided by 16. And I got 2.2 0.19 moles, all right? So that's basically how that is done. What's the next step? Divide right through by the smallest value. Which one is the smallest value? Right, so we're going to divide right through by 2.219 moles. So that means that this is 4.438 moles divided by 2.219 moles. Here it's 11.10 moles divided by 2.219 moles. And this divided by itself will give you 1, right? So let's see what the other two would give. 4.438 divided by 2.219, and that gives exactly 2. And then in the case of hydrogen, 11.10 divided by 2.219, and that gives 5.002, so that approximates to 5. So therefore, the empirical formula for this compound is equal to C2H5O. So that's the empirical formula. All right? Any questions about this? Any questions? Okay, so that was the B part. The C part is asking for the molecular formula. So if you remember, I said that in order for us to get the molecular formula based on the empirical formula, we need the integral factor. So how do we calculate the integral factor? The integral factor is calculated by dividing the molar mass of the compound by the empirical formula mass. Now the molar mass is given as 90, right? They gave you it in the form of the molecular mass, but we can use that same numerically for the molar mass. So this is how we go about doing that part. We have to, now remember the empirical formula was C2H5O, right? So what we have to do is find the empirical formula mass. So we do that by adding up all the molar masses of the elements according to that formula. So that's 2 times 12.01, and then we're going to add that to 5 times 1.008, and then we're going to add that to 16, and according to our calculation here, I got 45.06 grams per mole. So the integral factor, I, will be equal to the molar mass, which is given as 90 grams per mole, divided by 45.06 grams per mole. And let's see what that gives. 90 divided by 45.06, and that gives 2. So that means that the molecular formula will be equal to C2H5O multiplied by 2, which is equal to C4H10O2. And that's how that is done. All right. Any questions about this one? Okay. So, let me go back to the PowerPoint, see what's next. Okay, so that's it as far as combustion analysis is concerned. So the next we're going to talk about, again, this is a review, so I'm going to go through this rather quickly. Chemical equations, right? By now, we all should know what a chemical equation is. It's basically a shorthand way of representing what happens in a chemical reaction. And basically, what you'll have is the formula in a chemical equation. You're going to have the formula for the reactants on the left side of the equation. You're going to have the formula for the products on the right side of the equation. You're going to have an arrow pointing from left to right. And in some equations, to provide more information, they will give you information about the states of the different substances involved. So for example, in this particular reaction, we have S for solid, G for gas represented there, telling you the states of the different substances. So there are 4 states symbols that we use when it comes to writing down chemical equations. You have G for gas, L for liquid, S for solid, and AQ for aqueous, meaning that the substances are in an aqueous solution, all right? Some other piece of information might be added above or below the arrow in the equation. For example, if you see a triangle here, that tells you that basically you have to heat the products in order for the reaction to take place. In some cases, they will give you actual specific information, like the actual temperature, pressure, and other conditions. You might see something like a catalyst included as well, all right? So those are just some information that could be provided as well, just to give you some ideas to the type of conditions under which the reaction is occurring. Now, in order for the equation to quantitatively, accurately represent what is going on, basically we have to ensure that the equation is balanced. And we all know what that means, right? That means that in the equation, the number of atoms represented on both sides for each element must be equal, all right? So whenever it comes to, and by the way, that's important because of the conservation of mass law. If you remember, I think it was last chapter or the chapter before, the conservation of mass law says that in a chemical reaction, reactants, well, no material is lost or gained in a chemical reaction, all right? Or matter is not created nor destroyed. That's another way of expressing it, right? And the reason why that is true was something that was predicted according to the Dalton's theory, which basically says that the atoms themselves are not destroyed or created in a chemical reaction. So you have to make sure that you balance the equation properly so that any calculation based on it would be correct. Because if the equation is not balanced, then any subsequent calculations could be erroneous. Now, how do we balance equations? Well, the first two examples show you basically how not to balance equations, right? So for one, you cannot add an arbitrary atom on either side of the equation to balance any of the elements present or involved in a reaction. So like in this case here, this is the unbalanced equation right here, right? Because you have two oxygens here on this side and you have one oxygen here, right? What you cannot do is simply add an oxygen atom to this side to balance it, right? That would be incorrect. Another thing you cannot do is to actually change the formula of any substance in order to achieve that balance, which is what is done here, right? What was done here was that an oxygen atom was simply added to the structure of this molecule, which is a big no-no, all right? The only way you can balance equations is by making adjustments to the coefficients of the different substances involved. So to use this example as a simple example, we have two hydrogens here and we have two hydrogens here. So as far as the hydrogens are concerned, excuse me, they are balanced, right? But we have two oxygens here and we have only one here. So the question is, how do we balance the oxygens? And we do that by putting a 2 here to double the number of oxygen atoms on this side to be equal to those on this side. However, by putting a 2 here, we have also doubled the number of hydrogens here from 2 to 4. So that means that we need to put a 2 here in front of the H2 so as to achieve the balance of the hydrogens. And therefore now we have the balanced equation, which is the same as the equation that we have down here, all right? So that's basically how we go about balancing this particular equation, right? Okay, any questions about this? Any questions? So with that said, let me just go through some guidelines for balancing chemical equations. If an element is present in just one compound on each side of the equation, try balancing that element first. Balance any reactants or products that exist as free elements last. And in some reactions, you may have polyatomic ions which remain unchanged as you go from left to right. So you can, in most cases, treat that as one unit for the purposes of balancing the equation. And at times, you might have a situation where the only way the equation can be balanced is by using a fraction as a coefficient. However, the final answer should have integers, not fractions. So if you end up with a fraction, then what you should do is multiply by the appropriate integer so as to convert that fraction into an integer. And please note that the other integers or the other coefficients will be affected as well, all right? Okay, so let's look at some examples here. In the case of the first one, how do we balance this equation? Well, in this case here, you notice that there's one iron atom here. You have two iron atoms on this side. So what I would do is put a 2 here, right? And then I'll look at the oxygens. And what do I notice? I notice that we have 2 oxygens here and we have 3 here. So the question is, how do we balance the oxygens? Well, what I would do is I would multiply this by 3 over 2, right? And the reason why is because 3 over 2 times 2 gives you what? 3, which balances with the 3 oxygens here. However, this is not the final answer. What you have to do from here is that you have to multiply all of this by 2, all the coefficients here by 2. So when you do that, you're going to end up with 4 irons plus 3 O2 and then 2 Fe2O3. I'm sorry. So this should be Fe2O3, and that would be the final answer. And then what I would do, just to make sure everything is balanced, I'll do one quick check through, just to make sure everything is balanced. 4 ions on this side, 4 ions on this side, 3 times 2, 6 oxygens on this side, 2 times 3, 6 oxygens. All right, so now the equation is balanced. All right? Any questions about this one? Any questions? Okay, so how would you balance the next equation? Let me hear your ideas. Well,
There has to be at least 2 carbon dioxide because we have 2 carbons on the left side of the equation.
so if I hear you right, you're suggesting that I put a 2 here. Right?
Possibly.
Okay, no problem. Because of the 2 carbons here. Okay.
We need at least 3 H2O.
Okay, and the reason why is because you have 6 hydrogens here. So to make the 6, you put 3 here. Okay, very good. So the only element remained unbalanced would be the oxygens, right? So how would we deal with that?
You know, which oxygen we have on the right side, and it's
So how many oxygens do we have on the right side?
7, so we're
Sure.
gonna have to, on the right side of the equation, we have 2O2, which is 4 oxygen
Okay,
atoms.
very good, 7, yeah.
Yeah,
So how do we take care of that on the left side?
We're gonna have to times the carbon 2 or the C2H6 by 2 and readjust our carbon dioxide and water so that the oxygen is even so we can make O2 fit into it properly.
Okay. So I hear what you're saying and your approach is correct. What I would do is I'd multiply this by 7 over 2 to make that 7 oxygens, which balances with the 7 oxygens on the right. And then I'd multiply everything by 2. So that would be 2 C2H6 plus O2, 7 O2, I'm sorry, to give 4 CO2 plus 6 H2O, and that would be the final answer. And again, I'll do a quick check through to make sure everything is balanced. 4 carbons, 2 times 6, 12 hydrogens, 6 times 2, 12 hydrogens, and 14 oxygens, and 4 times 2, 8, and 6, 14. So all the atoms are balanced. All right? Any questions about this one? Okay, last one. Let me hear your ideas for the last one. Any ideas?
We're gonna need at least a 3 attached to the Na3PO4,
Sure about that?
because there's 3 Na. So we're gonna need at least a 3 attached to the NaCN, my bad, that's what I
Okay.
meant.
So put a 3 here. I would agree with that. Anything else?
You need to put a 3 in front of the hydrogen cyanide.
Exactly. And that's it. Everything else is balanced, so that would be the final answer. All right? Any questions about this one? Any questions? Okay, moving along. So the reason why, and I think I mentioned this before, the reason why you need to learn how to balance equations is basically that's what you need to do firstly before you do anything else whenever you're trying to solve a stoichiometric type problems, right? Remember, stoichiometry is that area which deals with the quantitative relationships between different substances involved in a balanced equation. Now, the reason why balancing an equation is important is because you need the correct coefficients for all the substances involved in the reaction. And the coefficients will give you the proportional relationship between the different substances in terms of moles, right? So basically, if you take any two substances involved in a chemical reaction, you can establish a conversion factor, which is the mole ratio between those two substances, right? So the mole ratio is a ratio of the coefficients of the different substances involved in, or the two substances involved in a chemical reaction, right? It's also called the stoichiometric factor, which is a term that I don't really use that much. So let's look at this simple example. The reaction between carbon monoxide and hydrogen to form methanol, right? The equation is balanced, so therefore you can identify the mole relationship between any two of the substances involved. So for example, you can look at the relationship between the carbon dioxide and the hydrogen. That's a 1:2 mole ratio. Or you can look at the relationship between the carbon monoxide and the methanol. That's also, well, not also, that's a 1:1 mole ratio. And then you can look at the relationship between the hydrogen and the methanol. That's a 2:1 mole ratio, right? So basically, that's how you get the mole ratios. And as you're going to see shortly, that's important for you to do certain calculations, right? So the mole ratios can be represented as conversion factors, as you can see here. So this is basically the conversion factor that is used to express the ratio between the carbon monoxide and the hydrogen, all right? And of course, you can flip this to get another mole ratio, all depending on, of course, the type of problem that you're solving. And here we see some other mole ratios here, which represents, or other conversion factors, which represents the mole ratios between carbon monoxide and methanol and hydrogen and methanol, all right? Now, in stoichiometric type problems, one key step that would be involved always in these problems is the mole-to-mole ratio between the different substances, right? So you could be given a problem where you start from a certain point and then you get to the moles of substance A, and then you need to get to the moles of substance B, and the way you carry out that particular calculation is based on the conversion factor derived from the coefficients of the substances involved in the reaction. And then also based on, or depending on the type of questions that you're given, you may need to convert moles of substance B into grams or other terms, all right? And I think the next slide is a simple example. Yes, okay, so in this case, fortunately for us, they gave us a balanced equation, right? So no problem there. What the question is asking for, well, the question gave you the 0.105 moles of propane. By the way, this is propane right here, all right? And then it says how many moles of oxygen are consumed, right? So what I would do is I'd start off with the 0.105 moles of C3H8, and then I'll multiply that by the mole ratio between the propane and the oxygen, right? Because the question is asking for the moles of oxygen. So based on the balanced equation, for every 1 mole of propane, the moles of oxygen would be 5 moles, right? So these numbers comes from the coefficient 5 and 1 here for the propane. So all we have to do now is calculate what this gives. So that's 0.105 times 5, and that gives, according to my calculation, 0.525 moles of oxygen. And that's it. All right? Any questions about this one? Any questions? It's a relatively simple example because you're doing basically a mole-to-mole type of calculation. All right? Okay, so, continuing. Okay, so this is basically an outline of the type of problem or the type of approach you'd take to solving a stoichiometric type problem, right? And it all depends again on how the question is worded. For example, the question may give you the balance equation and they gave you the grams of one substance, and then based on the equation, you're supposed to determine the grams of the other substance, right? So what you'd have to do is that you'd start off with the grams of, let's say, substance A, and convert it to moles, right? Of course, you do that by dividing by the molar mass. So that gives you the moles of substance A. Then we have to figure out the moles of substance B, and that's where this comes from, right? That's where this comes in, I should say. This comes from the balance equation, right? So when you multiply moles of substance A by this mole ratio, then you're going to get moles of substance B, right? And then, depending on what the question is asking for, the question may ask you for the mass in grams of substance B, in which case you'll multiply the moles of substance B by the molar mass, and that would give you the grams, right? So that's basically how we carry out this type of calculation. Now, here's a very interesting question being asked right here. It says, think, if we are given moles of substance A initially, do we need to convert A to grams, right? So in other words, if you have moles of substance A, do you need to convert moles of substance A to grams? And the answer is no, right? Because if you want to get grams of substance B, you don't need to go back up here and then go all the way down here to get what the question is asking for. Let's say the question is asking for the grams of substance B. Since you have the moles here already, all you have to do is the next step, where we convert from moles of A to moles of B by multiplying by this conversion factor, and then we follow that up with multiplying by the molar mass of B, and that will give you the mass in grams of B, all right? Okay, so that's basically an outline, and you're going to see this applied to problems such as these right here. Okay, so again, I'm going to need some space. And so let me copy this. Is it here? Okay, so this question says the final step in the production of nitric acid involves the reaction of nitrogen dioxide with water, and then it says nitrogen monoxide is also produced, and then it goes on to say how many grams of nitric acid are produced for every 100 grams of nitrogen dioxide that reacts. Okay, so folks, what would be the very first thing you need to do before you do anything else in order to answer this question? The first thing would be what?
Write out the reaction.
In other words, you need to figure out the balance equation, right? Okay, so in order for us to do that, we have to look at the information provided in the question and try to identify and write the formula of the reactants and the products. Remember now, the reactants will be on the left side of the equation and the products will be on the right side. So let me start with the reactants. What, based on the information provided in the question, what would be the reactants?
Nitrogen dioxide and water.
Nitrogen dioxide and water, okay? And then what would be the products?
Nitric acid,
Okay, so the formula for nitric acid is HNO3 and
Nitrogen monoxide.
exactly, NO. All right. Okay, so with that said, next step is to balance it, right? So how would we go about balancing this equation here?
We're gonna need at least a 2 in front of the NO2 on
Okay,
one
let's
side,
try that.
just at least.
Okay,
we need at least 2 in front of the nitric acid because
okay, let's try that. I'm sorry? Okay, Well, here's the problem with the nitrogen dioxide here, with the two here. That would be 3, and that would be,
It's 7 on one side.
I'm sorry, 2 and 1, 3 here, right? So you have 3 nitrogens on this side, you have 2 on this side. So what I'm going to do is put a 3 here. Let's see what that does. We have 3 nitrogens on both sides. We have 6 plus 1, 7 hydrogens. We have 6 plus, I'm not hydrogens, I'm sorry, oxygens. 6 plus 1, 7 oxygens. 2 times 3, 6 plus 1, 7 oxygens. And then for the hydrogen, we have 2 hydrogens. We have 2 hydrogens. So now the equation is balanced, right? So that's the first thing you need to do. You have to ensure that the equation is balanced. The next step is to now get into the actual math part of it. So according to the question, you have 100 grams, 100.0 grams of NO2. And the question is asking for how many grams of HNO3 will be produced. So what I would do is start off with 100.0 grams of NO2, and I would convert that to moles. So 1 mole of NO2 would go above, and the molar mass of NO2, so nitrogen is 14.01 times, or not times, plus 2 times oxygen, which is 16. And according to my calculation, that is 46.01 grams. And then the next conversion factor will express the mole ratio between the nitric acid and the NO2. So that's a 2 to 3 mole ratio. So I'm going to put 2 moles of HNO3 above and 3 moles of NO2 below. And then the final step is to convert from moles. Oh, by the way, this will cancel with that, NO2. Mole of NO2 will cancel with mole of NO2 there. And then the next step, the final step, is where we find the molar mass of HNO3. So hydrogen is 1.008 plus 14.01 plus 3 times 16, 48. So according to my calculation, the molar mass of nitric acid is 63.02 grams of HNO3. And down here would be 1 mole of HNO3. And then we work this out. So let's see what this gives. 100.0 divided by 46.01 times 2 divided by 3 times 63.02. So according to my calculation, when rounded off to 4 sig figs, it's going to be 91.31 grams of HNO3. All right? And that's basically how that is done. All right? Any questions about this? Any questions? Any questions? So this is a typical stoichiometric type problem. All right? And again, let me stress, before you do anything else, when it comes to these problems, you have to make sure that you have a balanced equation. All right? Okay, any questions about this? All right, I'm going to stop here for today, but I want to let you know, and I'm going to post an announcement about it later on today. Your first test will be next week, Friday. So not this Friday, the following Friday. And that test will be based on chapters 1 and 2 only. So what we're covering here in chapter 3 will not be on that test, right? And what I'm going to do is, right now, because some students from the other group asked about this, I'm going to post or publish some answer keys for past test number 1. Let me see here. Let me see what this have. Let me take a quick look at this one here. Oh, no, this is not. Oh, that's Chem 2. Crap. Okay, hold on. Don't know how that got there. Okay, this is. Oh, wait a minute. Try this one. Hold on, wait a minute. Am I looking at the wrong? How did these get there? All right, let me check out this one here. Ah, okay, I don't know how these Chem2 stuff got here. You know what? Let me try another folder. Okay, this should give some more promising. Oh. All right, I have to look into this, but I'm going to put some answer keys for test number 1 from past semesters. All right. So what I would recommend you do, and by the way, I haven't graded your assignment number 2 yet. I need to get on that as soon as possible. So I think I've graded your assignment number 1 and sent you your graded work, right? For assignment number 1. So I'm going to, if I've not done so yet, I'm going to post the answer key for assignment number 1. Let me just check this here. Okay, so let me okay, so let me publish this. And then let me check this out. So I'm going to publish the answer key for assignment number 1 right now. And as soon as I finish grading your assignment number 2, I'm going to publish that as well. So you can use that to help you to review for your test. All right. So I'm going to look for some past tests from previous semesters and upload it as well. And I'll make an announcement about that. All right. Yes, sir.
So in the files, I think I want to say under chemistry tables, there's a couple of pages dealing with common polyatomic ions. And there's a small table where it says polyatomic ions to memorize. Are we actually going to need to
No, you don't
memorize
need to
those?
memorize.
Okay.
Yeah, I don't believe in memorizing stuff like that.
It was like the nitrate acid.
Right. Those will be provided for you during your test, so you don't need to memorize those. I know some instructors require students to do that, but I don't. All right. So that's it. Unless there are any questions, you guys are. Oh, yes, ma'am.
Tables will like be in the test. We don't need to
We'll
print
provide
them
it.
out and bring them in.
No, you don't
ourselves.
print it. I'll provide it for you. All right. Okay. Any other questions? No. All right. So that's it for today, folks. I'll be available later on today for office hours if you have any questions. All right. And oh, let me get those who came in late. I'm sorry. Let's see. Anwar Afra, Anwar Afreen, Barner. Let's see. Davis, Jernigan. Talon is here. And Zaradka. Okay. Yes, ma'am.
I'm not gonna be here next week on Friday. Should I try and take the test like earlier on Monday, like when I'm able to take it on a different day?
Yeah, you can. I'm trying to think of Ooh, can you do it on either Monday or Wednesday between the hours of 2 to 5 during my office hours?
Yeah,
Hmm?
yes.
Hold on, let me check and make sure I'm telling you the right times. Yeah, 2 to 5, Monday and Wednesday. If that's okay. Now, you need to remind me, so send me an email like the day before,
Yeah.
so I can prepare for, for your test. All right?
Wednesday is preferred, so I can actually be here in class.
Okay, all right, cool. So, all right,
Thank
so, yeah, but make sure you email me and remind me.
The 2 to 5.
2 to 5, that's when I'll be in my office.
Thank you.
All right?
I'll email you.
All right. Okay, you guys out there in